Okay. So we just defined Fourier transform. And now we're going to play with this thing and slowly gain intuition about it and slowly gain why this transform is helpful.
זה משנה כאילו, כי יש כמה הגדרות הרי לטרנספורם פורייר.
אוקיי.
כאילו פה אנחנו בדרך כלל עובדים עם כזה שזה E במינוס IKX, ואז הטרנספורם ההופכי זה כאילו עם הפלוס. זה קריטי פה לעניין? איך מגדירים את זה? סתם כאילו בשביל להישאר ב...
Okay, so since you ask, we can of course, so the sign here is not, let me come with the next statement. After that, I'll address the issue of sign. So first of all, I want to mention that this Fourier transform is just maybe a couple of sentences. First of all, this Fourier transform is a linear transformation. So why is it a linear transformation? Because, well, if we compute Fourier transform of, I don't know, two functions, say alpha times f plus beta times g, this will be, of course, equal to alpha Fourier transform of f plus beta Fourier transform of g. So this will be symbolically alpha f tilde of k plus beta g tilde of k. So if I apply to a superposition of functions, Fourier transform acts linearly, and this property is probably obvious. If anybody who does not see this property, please send me a message and we will do. Is anybody for whom this property, the linearity of Fourier transform, is not obvious in the audience? Stop me here. Okay, so assume it's obvious. Good. Now it's not only linear transformation Fourier transform, it's also a reversible transformation. So if we have a function, if we know function f of k, and we put tilde over there to signify that it belongs to the functions in this space, we can find its inverse. We can find function f of x. So how we construct function f of x? Function f of x is an integral with respect to k divided by 2 pi from minus infinity to infinity. E in the power I k x f of k. So this is a, sorry, and here it's tilde. So if I know f of k, I can restore function f of x. So there are two sorts of function f of x and function f tilde of k, and I can go from one into another by Fourier transform, and I can go back by inverse Fourier transform. Okay, so now about the sign V. So sign of Fourier transform and inverse Fourier transform are opposite. So if one comes with a plus sign, another comes with a minus sign. So previously I should have defined it with a minus sign. And here I defined it with a plus sign. Now, why I defined it with this sign? Because in physics we know that in quantum mechanics there is a momentum operator, which you probably didn't learn or did learn. Okay, so which goes as minus I d over dx. So it means that when you apply an operator, which is a momentum operator, some function of x, it will be minus I d over dx that acts on the integral dk over 2 pi e I k x f tilde of k. So when this operator acts, it yields integral over dk over 2 pi, and here minus I times ik e in the power ikx f tilde of k. So this will be integral dk over 2 pi times k ei k x f of k. So it produces k. And this is exactly what we expect from the momentum operation. So therefore, we choose this sign such that it produces that the operator of momentum is labeled by k rather than minus k. So this is the convention that physicists prefer, but you can of course choose an alternative convention. Okay, so now next thing to discuss is that the inverse Fourier transform is indeed a inverse Fourier transform and its relation to Dirac delta function. So did you learn about Dirac delta function in your course on quantum mechanics? Okay, good. So let us now play with it a little bit. So let us see that Fourier transform and inverse Fourier transform are indeed an identity transformation. So if I apply Fourier transform and then inverse Fourier transform, or other way around, I didn't change the function. That's the point. So how do we see it? Okay, so let's apply both transforms. So I apply first Fourier transform to a function f of x. So this is the Fourier transform of a function f. And then I apply inverse Fourier transform. So if this works correctly, it should give me f of x. Okay, to be consistent, application of Fourier transform and inverse Fourier transform should not change things. So how does it work? So let me take this thing and rewrite it. So I take this left-hand side and I write it as an integral over, I change the order of integrals. I integrate from minus infinity to infinity x1, and the integral dk over 2 pi eik x minus x1 and f of x1. So I can write this thing. I can write this thing as an integral from minus infinity to infinity dx1 f of x1 times integral from minus infinity to infinity dk over 2 pi eik x minus x1. That's it. Okay, so now the claim is that this object, this integral, is just a Dirac delta function of x minus x1, and therefore the whole thing will be equal to the integral from minus infinity to infinity dx1 f of x1 delta x minus x1, and therefore would be equal to f of x. And now let's see why this is Dirac delta function slightly more carefully. So let's explore the integral from minus infinity to infinity dk over 2 pi eik x minus x1. Let's see how we understand this integral. Okay, so let me write this integral as an integral from minus infinity to 0 dk over 2 pi ek, and here I would write this I x minus x1 plus 0. And by 0, I mean some very small number that makes this integral to converge at k being minus infinity. Plus I add to this an integral plus an integral from 0 to infinity dk over 2 pi e k I x minus x1 minus 0. And once again, so I added a regularization that makes this integral to converge at k approaching infinity. Okay, then I can formally compute both integrals, and I get 1 over 2 pi e k I x minus x1 plus 0 I x minus x1 plus 0. And 0 is a 0, I understand, is an infinitesimal positive number. So it's infinitesimal and positive. So if you don't like 0, you can write, I don't know, something like this. Okay, so then this object is positive and approaches 0. Plus 1 over 2 pi e k I x minus x1 minus eta I x minus x1 minus delta eta. This goes from minus infinity to 0. This goes from infinity, from 0 to infinity. Okay, now what it allows us, since we introduced this regularization, that at plus minus infinities, this term would vanish because there's exponent of some negative infinite number. And therefore, we end up with contribution that looks like 1 over 2 pi I, 1 x minus x1 minus I eta minus 1 over x minus x1 plus I eta, where this eta is positive and approaches 0. Okay, so now let's look at this function. Let's look at this function, how this function looks. So this is actually, we can combine both terms and see that it's 1 over pi eta divided by x minus x1 square plus eta square. So what is this function? How does it look? So first of all, if eta is finite, it's actually Lorentzian, yeah? The height of this Lorentzian is 1 over eta. And, okay, sorry, I should have, let me take it back. So this is indeed Lorentzian, but it's Lorentzian at, so if this is the x, I don't know, x1, so this is the point x. So it's Lorentzian peaked at point x. So the height of this Lorentzian is 1 over eta. And the width of this Lorentzian is eta. So if I want to compute the area underneath this Lorentzian, that it's something that has a width eta and height 1 over eta. So the area underneath this Lorentzian is just 1, as it should be for delta function. Now the width of this thing, the width of this Lorentzian is eta, and therefore when eta approaches 0, this width is infinitely sharp. It's very narrow, and therefore that thing is a delta function. So the integral with respect to variable x1 of this object should be understood as following. So it's a very narrow function. Therefore, I can replace in function f of x1, I can replace x1 with x and say that this is approximately f of x times integral over dx1, 1 over pi eta x minus x1 square plus eta square. But this integral is just 1, and therefore we end up with f of x. In the limit of eta goes to 0. So what we more or less learned, that we had a term that looked like 1 over x minus x1 plus I0, sorry, minus I0 minus 1 over x minus x1 plus I0 1 over 2 pi I, and we have seen that this is essentially a delta function of x minus x1. So what we can extract from this, that if we have a thing that looks like x minus x1 minus I0, it's essentially minus pi I times delta function of x minus x1 plus the principal value of the x minus x1. And if we have 1 over x minus x1 plus I0, it must be complex conjugated. So it's pi I delta x minus x1 plus principal value of x minus x1. So if we subtract, let me use different color, if we subtract this thing from that thing, then we will get 1 over x minus x1 minus I0 minus 1 over x minus x1 plus I0. We will get, sorry, here should be a plus sign, and here should be a minus. Then we'll get 2 pi I delta function of x minus x1. And if we add these two things together, x minus x1 plus I0 plus 1 over x minus x1 minus I0 plus I0, we will get 2 principal values of x minus x1. So these relations are sometimes known as Sahotsky Plimelj theorem. Okay, so we learned two things right now. We learned that there is a representation of delta function as a difference of these terms. And we also learned that this difference precisely emerges in the computation of inverse Fourier transform, and therefore inverse Fourier transform really inverts the Fourier transform. Okay, any questions so far? Okay, if everybody understands everything, let's compute some simple examples. So let's take a function f of x, which is something very simple, like 1 over x squared plus 1, and let's compute its Fourier transform. This is something that we need to compute. Okay, so let's us do it. So Fourier transform of this function is just by definition integral over x, f of x e into power minus I kx. So this would be integral over dx e minus I kx x squared plus 1. How we compute this integral? And the answer should be pretty obvious by now, because that was an idea that repeated itself many times during this course. How do we compute an integral like that? Exactly, yeah, exactly. That's what we do. So we just look at its complex. It's a structure on a complex plane, and the structure on the complex plane is pretty obvious. Minus ikx, x plus I, x minus I. So if I draw this function on the complex plane, it has two poles, one at the point minus I, and as is the point I. So I need to compute an integral along the real axis. So this is a complex AX plane. So x became a complex variable, and my integral goes along the real axis. Now I of course can use Cauchy theorem, but to use Cauchy theorem, I need to close my integrals at the infinity to make this line to be a closed loop. How can I close this loop? And now notice an important detail, that there is a function exponent of ikx. So this function, if I'm gonna take x into the imaginary direction, this function would be either exponentially large or exponentially small. So if x acquires some imaginary part, so whatever stays in the exponent will be either exponentially large or exponentially small, depending on the sign of k. So let's assume for a second, or study the case when k is positive. So k is real and positive. So if k is real and positive, then minus ikx will decay in the lower, or not decays, what is the right word? It's negative, is negative, yeah, is negative in lower half plane. So imagine that I take x to be somewhere here in the lower half plane. So I have minus ik, and x would be something minus I times something positive, yeah? Then this thing will be k times x times minus 1. And this will be smaller than 0. And this will be in the exponent. Therefore, this thing will be exponentially small. The conclusion is that if k is positive, then I can close this integral in the lower half plane. And the part on this very large circle is exponentially small. So if I make this circle semicircle exponentially large, I get the result with exponential accuracy. Okay, so let us just do it. So let us consider this positive k and close the integral in the lower part of the complex plane. Then I get minus 2 pi I. That's because I closed it in this thing. And the contribution that I'm picking is the contribution from the pole minus I. So therefore, it will be minus 2 pi I. Here, I will get minus 2i, and here I'll get e in the power minus I times k. So altogether will be p pi e in the power minus k, and this here we assume that k is positive. Any questions so far?
זה כאילו אתה מראה מה קורה על העקומה בעצם, החישוב הזה למטה?
No.
זה פשוט החישוב.
No, that's a computation of this of this integral is under the assuming that k is positive. So if k is positive, I'm completing this a line of integration into a closed loop that passes through the entire plane and use the Cauchy theorem to compute this integral, and that's the result. So what do I do when k is negative? So now let's do the same when k is negative. So what would we do? Exactly, I'm doing the same, but now let me use a different color. So now I'm doing the same, but I'm closing this integral in there. So this will be the closure for negative k. So now the direction has changed and I'm picking a different pole. Now I'm picking a pole at I, and the direction is now counterclockwise. So then I'm getting f of k to be 2 pi I, because now the direction is counterclockwise, in the power minus I ki over 2I, and I'm getting pi e in the power k. So this is k negative. Now I can look at these two answers and combine them together and say that for all k's, for all values of k, the Fourier transform can be written as pi exponent of minus absolute value of k, both positive and negative. So when k is negative, I end up with exponent of k, which is a negative number, and when k is positive, I wind up with exponent of k, which is also a negative number. So I always end up having a negative number in the exponent. So what I just computed, I computed a Fourier transform of a Lorentzian. I computed a Fourier transform of a Lorentzian, something that was Lorentzian in the X space, and it became exponentially decaying function. So if I now draw this function in the K space, so this function in the K space looks like this. It has so this is a function f. So this is this function. It has a cusp at k equals 0, and it exponentially decaying as a function of k. Okay, it's an example of Fourier transform computation. Next, okay, so let's take another function and compute another example. So another example of computing Fourier transforms. Let's take a function f of x, which is exponent minus x squared over 2a. This function is called Gaussian. So in X space, it describes this function looks like this, and it has a width, and its width is square root of a. So it's something which is also exponentially localized. It's a Gaussian, and the width of this Gaussian is a. Okay, but now we'll see it. Okay, yes, but now we'll see it. Yeah. Yes, all what you say is correct. All what you say is correct. Yeah, obviously, yeah. So let's just look at, let's just see it, yeah. Nothing what I'm saying is, I don't know, is a new or discovering. It's something that everything is very well known, but I just want to to put it in the context of complex analysis and explain how we compute these things using complex variables. Okay, so e in the power minus I kx minus x squared over 2a. Okay, so how do we compute this integral?
We complete the square.
Yeah, we completed the square. So let's do it like this. Dx exponent minus, okay, so that will be x over square root of 2a. So here we need to assume that a is positive. Otherwise, this integral diverges, plus I to square root of 2a divided by 2 times k square minus ak square over 2. Okay, so then we can write this object is e in the power minus ik square over 2 times an integral dx running from minus infinity to plus infinity e minus x over 2a plus I square root of 2a over 2 times k square. Okay, so what is the next step? The next step is to say that let's call the entire object here, let's call it x tilde, and the integral with respect, so this thing will be now e minus ak square over 2 square root of 2a integral dx tilde e minus x tilde square, but now the integral with respect to x tilde runs along this line. It's no longer runs again along the real axis because we have shifted it by square root of by this much. But now we know that in complex analysis we're allowed to move the contour of integrals as long as this thing does not cross any singularities. So therefore we are allowed to take this contour and move it back and make this integral to go from minus infinity and infinity without changing the value of integral. So then we left to compute this integral. Okay, how we compute this thing? How we compute this thing? Yes, that's of course correct, but how we compute this constant?
We calculate if we call this I, we calculate I squared.
Okay, so let's calculate I square. So I square will be integral over dx in the power minus x square times the same integral, and let's call it y, right? And then we say this integral, it's dx dy in the power minus x square plus y square. And then we say, okay, so let's look at this as a two-dimensional integral. X and y are coordinates, and let's go into the polar variables. So let's define polar variables. So now it will be an angle phi and radius vector r. So this will become an integral over d phi from 0 to 2 pi, and the integral from 0 to infinity r dr, exponent of minus dr, exponent of the minus r square. And then this part of integral yields 2 pi. So we end up having 2 pi integral from 0 to infinity r dr, exponent of minus r square, which we can write as 2 pi integral over dr square over 2 e minus r square from 0 to infinity. Now let's call it r square by a new name. So then this integral becomes 2 pi 1/2 integral from 0 to infinity dxi e to the power minus xi. But this integral we already know how to compute it. 2 pi divided by 2 e in the power minus xi with the minus sign. From 0 to infinity. At infinity it vanishes. So we are having 2 pi over 2 and the value of this integral at 0, which is just 1. So we end up with pi. Therefore, I square is equal to pi. And therefore, I is equal square root of pi. And therefore, Fourier transform, we have computed, is equal to 2 pi a square root e minus a k square over 2. So we started with a function f of x, which was e in the power minus x square over 2a, which was one Gaussian. And so this was a Gaussian in an X space. And the width of this Gaussian was square root of a. Because this is where x square over 2a was roughly 1. So x was roughly 2a square root. Now, if I look at the Fourier space, and I draw f tilde of k, it's once again a Gaussian, but this time it's a Gaussian of different widths. So it has a k square over 2. It's equal to 1, so it roughly means that k is 1 over square root of a. So this time the width of this Gaussian is 1 over the width of the original Gaussian, as you said at the beginning. Okay, but now we saw it explicitly. Okay, so this was more or less the definition of Fourier transform and few basic examples how we compute it. Now we come to the natural point. Why do we define Fourier transform? Why is it helpful in any way? Why this thing is useful? Because of course we can define anything we want, but the question is, if we define something, is it going to be useful? Okay, and the answer is obviously yes. And the main advantage of Fourier transform comes from the computing the differential, comes from differential equations. So assume that we have some ordinary differential equation in terms of function f, something that has terms like df over dx times some constant plus d2f over dx squared plus some other constant dn over f over dx in the power n. And there is some function on the right-hand side, I don't know, g of x. So this is a ordinary differential equation of nth order for the function f. And what is important here is that all coefficients in these equations are constant. That's the simplest case, and I think this is the most illuminating case where advantage of Fourier transform is obvious. So of course you can solve this equation directly as you always solve differential equation, but you can also do the following: you can apply Fourier transform to this equation. So let's Fourier transform this equation, left side of this equation and the right side of this equation. So we'll have a Fourier transform of all these functions. will be equal to Fourier transform of the right-hand side. But now remember that Fourier transform is a linear operation. So what it implies that we can write the left-hand side actually as a Fourier transform of df over dx plus c1 Fourier transform of d2f over dx squared plus cn Fourier transform of dnf over dxn, and will be equal to the Fourier transform of the right-hand side, which we can call g of k. Okay, but now there is a property of Fourier transform that Fourier transform acts very simple, in a very simple way on the derivative. So what does it do? Let's compute a Fourier transform of a derivative. So it's d over dx f of x, and I'm now Fourier transforming this guy. So what is actually written here? It's df as a differential times e minus I kx running from minus infinity to infinity. So I can always write it as f of x e minus I kx from minus infinity to infinity minus f of x applying differential to the second function. So what it means that I have this guy at the boundaries minus f of x e minus I kx times minus I k dx. Now assume for a second that f of plus minus infinity is 0. So function f of x vanishes at the boundaries. Then what I'm getting ik integral e minus I kx dx f of x. But this guy was just defined as a Fourier transform of f of x. And we denote it as f tilde of k. So this means that we are getting minus ik f tilde of k. I got a minus sign wrong, just a sec. Just a sec, or maybe I didn't.
But didn't we do this at the start of the lecture with the p operator? We didn't do this. We didn't integrate by parts. We simply differentiated by x.
Yeah, so let's check the sign. So I'm getting d over dx is equal to minus ik. So if I multiply it by, no, I'm getting a wrong sign here because I want, so now I'm getting minus, now I'm getting minus I d over dx is equal to minus k, right? And I should be getting plus k, so just somewhere is a trivial mistake here. So let me look back at the definition. So I'm Fourier transforming, and we agree that we Fourier transform with minus ikx. Yes, Fourier transform is minus ikx. Then here is a minus sign.
There's a minus sign for differentiating the exponents, right?
Yeah. So here it's already is a plus sign. So I don't know why did I write here a minus sign. No, so up to here everything was correct, and this is just ik times the Fourier transform of function f of k. So there's no reason to write minus here. It's a plus. So it means that d over dx generate ik, and it means that minus I d over dx generates k. So that's exactly what we said at the beginning of today's lecture. Okay, so that's consistent. So of course now I can play this similar thing and compute Fourier transform of second derivative of the function f of x. And I do exactly the same. I'm computing integral from minus infinity to infinity dx d2 over dx square f of x e minus ikx. And I'm saying, okay, but this is integral. This is a derivative of df of x over dx times e minus ikx from minus infinity to infinity. This will be now equal to boundary term minus integral df over dx d e minus ikx. Now, neglecting the boundary term, assuming that it does not exist, we are getting that this is minus df x over dx minus ik e minus ikx dx, which is equal to minus 1 minus ik integral df of x over dx e minus ikx dx. So this would be equal to ik times Fourier transform of df of x over dx, which we computed a few minutes ago. So we know that this will be equal to ik times ik times Fourier transform of f. So we are getting I in the power k square f tilde of k. Now we can, of course, generalize this proof and show that Fourier transform of df of x derivative of nth order will yield just ik in the power n Fourier transform of the function f. So essentially, under Fourier transform, derivative with respect to x generates I times k. Sometimes x and k are called conjugate variables. So d over dx in the power n corresponds to I times k in the order n. So what does it mean? It means that if we started with our differential equation above, so here was a differential equation, this equation essentially becomes an algebraic equation, because what it really means, let me write on top of it, that now this equation means C0 times ik plus C1 ik square plus Cn ik in the power n. All this multiplied by f tilde of k is equal to g tilde of k. And therefore, I can, in one line, solve this equation. I can say that f tilde of k will be equal to g tilde of k divided by C0 ik plus C1 ik square plus so on Cn ik in the power n. So it means that I already know the Fourier, my function f in the Fourier representation, or in other words, the Fourier transform of the function f of x. So what is left to do, if I want to compute f of x, I need to compute inverse Fourier transform of the function f of k. And we agree that this is inverse Fourier transform is just an integral over dk over 2 pi ei k x f tilde of k. So I take this guy, I substitute it here, and compute a Fourier transform. And this automatically solves a differential equation, ordinary differential equation with constant coefficients of any order. Okay, so let's do some very simple example right now, and in the exercise session with Yoni, you will do more complicated examples of this type. But let me do the first very simple example just to give you an idea how it works. So let's compute something very simple. Let's solve differential equation df over dx is equal to theta function of x times e minus x, assuming that eta is something positive. So it's and we need some boundary condition plus some boundary conditions. For example, let us consider boundary conditions that f of x is equal to 0 for x smaller than 0. So there was a function that for negative x was 0, and then it obeys this differential equation. Of the first order. Now, how do we solve this equation? So of course, the easiest way to solve this equation is just solve it directly, because this equation is very simple. I choose it on purpose. So what is the solution that we normally do? We would say that f of x is an integral over dx1 from minus infinity to x of the thing that stays on the right-hand side of this equation, namely theta of x1 eta minus x1. That's just by immediately the solution of this thing. So let us finish this computation. So this would be equal to the integral from 0 to x dx1 e minus x1, and this will be equal to e minus eta x1 divided by minus eta from 0 to x, and this yields 1 minus e minus x divided by eta. So how does it look? This f of x as a function of x. So here at x equals 0, this function vanishes. At very large values of x, this function approaches value of 1 over eta. There is a typical x which is equal 1 over eta. So when x is smaller than this thing, it's close to 0, and when it's larger than this, it approaches a constant. So it's something like this. Okay, so now let us get this result, this quite obvious computation, by using Fourier transform, the ideas of Fourier transform. Okay, so let's once again write an equation. Gf of x over gx is equal to theta of x e minus. Okay, so let's Fourier transform. So we have Fourier transform of gf of x over gx should be equal to the Fourier transform of theta function of x e minus theta x. Okay, so Fourier transform of the left-hand side, we know what it is, right? What is this thing?
ik f tilde
ik
of x
f
of k.
tilde of k, yes. So now we need to compute the right-hand side, which will be integral from minus infinity to infinity dx theta function of x e minus ikx minus eta x. And we compute this integral and we get this is equal to 1 ik plus eta. So now we have an equation ik f tilde of k is equal to 1 over ik plus eta, which means that f tilde of k is equal to 1 over ik times ik plus eta, which we can also write as 1 over k divided by k minus I eta and the minus sign. Okay. Now we want to get it in the x representation. So what should we do? We should compute an inverse Fourier transform. And here there is one point that worth thinking about. So f of x, and I'll show you. So this is an integral dk over 2 pi eikx, k runs from minus infinity to infinity, of f tilde of k. Now we just plug it in, dk over 2 pi minus infinity to infinity, eikx, all this is very good, 1 over k times k minus I. Okay, so now we know by heart how we compute these integrals. We draw a complex plane, and this is the complex plane of k. And now we need to do two things. We know that we have something that looks almost like a closed contour. This is the integral that goes along the real axis. This is the integral of k that goes from minus to plus infinity. So there are two things that we need to bear in mind. Obviously this function has only pole-like singularities. So we need to understand how we close the contour and what singularities are falling into the part of the contour that we closed. Now, we know that our boundary condition was that the function f of x, so we know that f of x was 0 for negative x, right? So this property is better be respected when they compute this integral. So it means that if x is negative, we should be able to close this contour in a way that no poles are falling into the contour. Right? Now there are two poles here of this function. So what are these poles? Correct. So there are two potential points. There is a point which is called I eta, and another thing which is called 0. And about I eta, there is no equation. It belongs to the upper half plane. But about 0, something is not fully completely defined in this integral because it just lies on the line of integration and things are not yet defined. We were not sufficiently accurate in playing with these things. And now it's a moment to stop and think where this 0 actually lies. So now if we want that x smaller than 0, that for x smaller than 0 this integral vanish, it means that we should be able to close the contour of integration for negative x without picking any poles. So if x is negative, where can we close the contour of integral? We have exponent of ikx. K, we can either close it like this, or we can close it like that. There are two options.
נכון, אבל זה אמרנו שזה תלוי אם אנחנו הולכים כחיובי או שלילי.
No, this is an integral. Look, this is the integral over K. Don't to be confused with the integral with respect to X. So what determines the choice of a half plane?
אז אוקיי, אז אם X שלילי,
אם X שלילי,
אז זה אומר שאנחנו רוצים לקחת K'ים שיגרמו לזה להתאפס, אז בחצי החיובי.
הכל נכון, רק הפוך, אז בחצי השלילי. אם X שלילי,
כן, אז אני רוצה K'ים חיוביים כדי שהאקספוננט כאילו ילך לאפס, לא?
בוא ניקח. X שלילי, בוא נכתוב את זה, אז יש לנו באקספוננט יש לנו IKX. אנחנו יודעים ש-X שלילי, אז בוא נכתוב את זה I כפול מינוס כפול absolute value של X כפול K. אוקיי, עכשיו אם ל-K, בוא נכתוב ש-K יש איזשהו I כפול משהו שהוא חיובי. ונציב את זה פה, אנחנו נקבל מינוס I כפול X כפול K, ולכן אנחנו נקבל כפול X כפול K, וזה משהו חיובי, ואם אנחנו ב-K'ים גדולים זה מתבדר. לכן אנחנו רוצים לבחור, לכן אם X הוא שלילי, אנחנו רוצים לקחת את ה-K'ים גם כן שלילים. ולכן אני מקבל פה משהו שלילי, ולכן משהו שלילי וגדול עומד באקספוננטה, והאינטגרל שלי מתכנס. ולכן עם X שלילי, אני בוחר את הקונטור בדיוק כמו שציירתי, כמו קונטור הירוק. אוקיי? אז אני בוחר את הקונטור כקונטור הירוק, ואני יודע שבמקרה הזה אני לא רוצה, I don't want to pick any poles. So it means that actually,
we're making a small circle around the point zero.
No, just, where did I go? No. Sorry, I wanna restore. No, just okay. Let me. It's easier to draw from very beginning. Okay. So I have this thing. This is my axis. This is my another axis. This is my another axis. This axis. So there is this pole, and then this point at 0, I'll shift it there, such that now I have two options. Option number 1, like this, and option number 2, like that. So if this is the pole at 0, so this is a pole at 0 that I pushed up a little bit, up into the upper half plane. So I modified this thing and I added here plus I0. Sorry, I want this thing to be in upper half plane, so minus I0 here. So I pushed it up. Minus I0, yes. So let me modify this pole. I creatively replace it by this, pushing this thing, pushing both poles, both I theta and 0 into the upper half plane. So now they both lie in the upper half plane. So when X is negative, I pick no poles, and therefore for negative X, my function, my result is just 0, because I close the integral in the half plane first, no poles. And for X greater than 0, I'm now using the purple loop. And okay, now I have two poles here, 0. So this is K equals 0 and iota. And therefore I'm getting result which looks like f of X is 2 pi I. It's a counterclockwise, 1 over 2 pi And here I'm getting 1 over minus I eta. This is from k equals 0 pole plus e minus eta x over I eta. This is from k equal I eta pole. And all things together give me 1 minus e in the eta x divided by eta. Lo and behold, the same result we knew we will get from a very simple solution without any Fourier transforms. So here it looked like Fourier transform enable us to get the right result. We had to think on the way more than we normally do when we solve ordinary differential equation. However, as you will soon see, Fourier transforms allow us to solve much more complicated equations. Equation that brute force solution is way more difficult than computing Fourier transforms. So once you master Fourier transforms, you will be able to solve these and more complicated differential equations in a very straightforward way. So that essentially means that you map the problem of differential equation to the computing Fourier transforms, and Fourier transforms is essentially the same as computing integrals via Cauchy theorem. So if you master complex analysis and you know how to compute integrals from minus to plus infinity using Cauchy theorem, then all these three problems are essentially identical: solving differential equations, computing Fourier transforms, and using Cauchy theorem. It's the same. It's essentially the same problem. Okay, people, I think I'm done for today. So it's time left for questions. So if you have any questions about today's lecture, please go ahead.
Well, how can we move the singularity up? We could have just as well moved it down and gotten a wrong result.
Okay, so with singularity, you should be extremely careful. Yeah, so every time you have a singularity that seemingly lies on the contour of integration, it's a moment to pause and think. Because if there is a singularity on the contour, that strictly speaking, something in this procedure is ill-defined. And it's ill-defined because we were not very careful in what we did. And probably there is a way to be completely mathematically kosher and do everything in an absolutely kosher way, but nobody ever uses it. So if you have a singularity, you need to understand what is it, and that's why I gave this particular example just to illustrate this idea that this issue always arises when you use Fourier transform for solving differential equation, because when we computed Fourier transform, it did not know what was the boundary condition. Yeah, so I formulated a boundary condition such that the solution was 0 for negative x. I could have stated an opposite problem. I could have stated, please find the solution of the same differential equation, but with the boundary solution, but with the boundary condition that solution vanishes for the positive value of x. Yeah. And then the same singularity should be treated in a completely different manner. So when I computed a Fourier transform, I did not thought twice about boundary conditions. I did not pick any boundary terms from the plus or minus infinity. I just said, let's Fourier transform it in a very naive way, and then decide where to put singularity. So I Fourier transform my equation without thinking about boundary conditions, and then say, let us look at this singularity and let's think whether we should or should not pick it depending on the boundary condition I've chosen. Yeah. Of course, you could be more careful and more cautious and then say, okay, when I Fourier transform this thing, I can go back and Fourier transform this thing. And I have my function f of x. When I compute it, I should be very careful about boundary terms. Boundary terms where this function vanishes at plus or minus infinity. And then this boundary term will appear. I can regularize this integral on this level. And then I will most definitely generate a corresponding shift of the singularity from 0 to, in the complex plane, to the point where it should be shifted. So you can be very cautious and do this Fourier transform, thinking that actually my function f of x is something that we define to vanish at where we define to vanish at negative x, yeah. So therefore, what when I will compute this Fourier transform, I need to remember that I might generate some divergence at positive x, so I better regularize this thing properly. And so you either remember about this regularization and then you generate some boundary term here, or you don't bother, but then when you go back, you need to interpret this singularity correctly and place it either within or outside the contour of integration. Now it's up to you. I did it in the way that I just use Fourier transform the same way for any boundary condition. I can use it for the problem where a function vanishes for positive x or for negative x, and then I Fourier transform back. I decide what to do with my singularities that come to lie on the contour of integration. But you can, of course, think about boundary terms when you Fourier transform and then shift these points from the very beginning by making all integrals converge. Okay, any other questions?
שאלה של הלו"ז, שבוע הבא אין שיעור, נכון? בגלל הצום. אז זה כאילו השיעור האחרון שלנו.
אין שיעור שבוע הבא, זה משהו חדש בשבילי, אני חשבתי שהולך להיות שיעור הבא.
לא יודעת, ראיתי בלו"ז של האוניברסיטה שב-27 שזה יום ראשון.
באמת?
טוב, כן, אז בגלל זה אני כאילו, אולי יש לך דברים אחרונים להגיד, אני לא יודעת, כאילו, אז...
Look, I was thinking about giving one more lecture about Laplace transform. Now, it's very similar to Fourier transform, but with the problem that it's very similar to Fourier transform, but with the problem when you have a boundary condition at something like you have initial value boundary condition rather than so it's essentially a problem when you have some differential equation, say in time domain, and you formulate the initial value boundary condition at time equals 0. So this is another type of transform which is very helpful, and I was thinking about giving the last lecture on this transform. Now we need to understand if there is a cancellation of the last lecture, I don't mind giving this lecture some other time, yeah, if you want to hear about Laplace transform. Of course, the easiest thing for me is not to do anything. But if you're interested, I'm willing to prepare one more lecture on Laplace transform and give it during a time where there is no constraints and problems. So you need to decide. It's
אני בעד, אבל צריך לשאול את כולם.
אני לא שומע.
אני אומרת שאני בעד, אבל אני לא מחליטה על כולם, אז צריך
Okay, so you need, people, you need, okay, so why wouldn't you discuss it between yourself and come to the conclusion when it's appropriate from your perspective to from your perspective to be to have one more lecture. I have no constraints next week, so practically any day will be fine. So whenever you can come, I'm willing to give one more lecture on Laplace transform, either on Sunday or any other day. So that's all what I have to say.
השאלה חומר שהוא יהיה במבחן הטרנספורם לפלס.
Up to you. If you want it to be part of the exam, it's fine with me.
הסמסטר נגמר שבוע הבא, אז כאילו לא יודע מתי נוכל למצוא לזה זמן. זה העניין.
Okay, people, you decide. I can teach it and not make it part of the exam. I can teach it and make it to be part of the exam. I honestly don't care, because for me, it's the same. It's up to you. It's something that I think is useful, and you may find it useful. If you want to learn it, I'm willing to teach you. If you don't want to learn it, it's fine with me. You want it to be part of the exam, fine. If you don't want to be this part of the exam, it's also fine. There are so many possible questions that I can ask for the exam that it makes absolutely no difference. And it makes things no easier, no more difficult. It's plays no role. Yeah? Okay, anything else? So you just inform me what you decided. If you decided to have one more lecture, I'm willing to teach one more lecture. If you don't want to learn Laplace transform, I'm happy not to prepare. For me, it's easier, obviously, not to teach than to teach. But like I said, I'm willing to teach because I think you may need it. So if there's no more questions or comments.
Could you just remind, I'm searching where you did it in the second example for when we did the Fourier transform of the Lorentzian. We moved the contour of integration in the complex plane.
Yes.
Could you just remind why we're able to do it?
Well, because there's no singularities that we're crossing. So we're allowed to move contour of integration as long as we don't cross any singularities.
Mm-hmm.
So if you have a contour of integration that was essentially closed loop, starting at the point at infinity and ending at the point of infinity. Yeah? So the real axis is a closed loop that goes from the point infinity to point infinity. So I did not change that point, and I shifted the integral. So all points at infinity are the same. It's really one point. We know it. We know this song by now. So we shifted this integral without crossing any singularities, and that's fine. As long as we don't cross any singularity. Now, singularity of this function, it's a good point. So where's the singularity of this function exponent of minus x squared? Where's the singularity of this object?
Well, it's sort of at infinity, isn't it?
Yes, it's an infinity. And therefore, when we moved it, we did not cross that singularity. It was no singularity between point I square root of 2a and 0. So, sorry, point I square root of 2ak and 0, so we could shift it without crossing any singularity, and therefore we did not change the integral. So complex analysis about the Cauchy theorem is always about the statement you can deform the contour of integration as long as you don't cross any singularities or touch any singularities, the integrals are unchanged.
Okay.
Okay,
Thank
תודה,
you.
דימה.
בבקשה.